So, we had some discussions about what to do with it, and I will remind you that the reason that we're doing homework is to get practice, right? So, and the other thing is, I don't want to waste your time, okay? But I also want, and I want to give you credit for the work that you're doing. Sometimes the mastery physics can be useful to you, and sometimes it's not quite so useful, okay? So I consider it to be good when it gives you some hints and helps you work through something, or at least lets you know that you successfully completed, some of the problems, okay? That's a win. You gain some confidence. You're pretty sure you did something right, okay? It's not a win if you're struggling with it. It's being very picky about its the number of decimal places or certain constants or something, and you have the right technique, but it's blocking you from moving forward, okay? So there was an idea that perhaps I could reduce the number of problems, okay? But there's an issue with that. I've already, it turns out that they give a lot of problems, and I already cut them back. And if I cut them back too much, then you haven't seen the different, if I, in an extreme, if I ask, say, 5 problems, per chapter, there'd be a whole lot of stuff you hadn't seen, and that would not be good, okay? And if my goal is to reduce the number of problems that are a pain in the butt for you, but keep the ones that are working for you, I don't know which ones those are because each of you are different, okay? So the summer rule will be if you can get 75% of the mastering physics done, I will give you full credit, okay? So if you get, and I would say also, if you're really getting stuck on a problem, okay, your strategy should always be work on something. If you don't have it, or at least think you're pretty close, within half an hour, move on to something else, okay? And get help with, why am I stuck? You can talk to other people. It's great. The best thing possible is to work with other people, okay? The next best thing is to get help through some other means. If you want to ask me a question, or you can send an email. You can send an email with a JPEG. Say, this is what I was thinking. Is this the right track? Is it going to lead to a solution? I will answer those questions. Same rule with looking at lab drafts. I'll get to you within 24 hours. Okay, but I will try to get back with you, and sometimes while we're doing this, I'll be working on something. I will respond. If you're around, we might end up having a small conversation through email. And I found that in a lot of cases, people can get unblocked. In some cases, it doesn't work, and it's probably best to meet up. But you might as well at least give it a try. Okay. The worst thing to do is sit and struggle with a problem that is you don't know what to do, you're going nowhere, and you just bang your head against it for hours. I've heard people say, I spent 4 hours on that problem and I got nowhere. And I'm like, I wish you'd spent half an hour on that problem and gone nowhere. Because the other 3.5 hours were just making you mad. They weren't really helping you learn physics, right? So try, okay, and if everything's hitting you hard like that, then we need to figure out a way to make it go smoother, okay? But if it's just one of the problems that's really driving you nuts and you move on and you do other stuff, you may find when you come back to it later, it looks a little better, or, anyway. Okay, so my goal with this 75% is if one of these problems or a couple of the problems are driving you nuts and they're not going anywhere and you're up against the wall and you got to get it done, go ahead and hit it in. Okay, you've done your effort. Okay, I still think it's a good idea to look at at all the problems. Oh, the other thing you might do is you might look at one problem and you might say, I know I can do that in 20 minutes, and these are not the types of problems I'm having difficulties with. If I go through mastering physics, I'm going to spend 20 minutes answering a bunch of stupid little questions, and I'd rather move on to the stuff that's going to, I don't want to waste my time. Okay? So that would be a legitimate thing. I'm going to skip that one and move on. Now, a number of things could happen. You could move on to the other problems, and you could go, all right, these are more difficult problems. I'm doing well with them, and I'm glad I skipped that one. Okay? Or you might go into the further problems, and you might go, oh, I'm not doing well with these. Then you can go back and do the one you skipped. You thought maybe you knew it, but maybe you didn't. So use it as a tool to get things done on time. Don't use it to skip. To say I'm just going to do 75% of this because that's good enough. It's more like, no, we're under time pressure. We don't have what we normally have during the rest of the year. Use it as a tool to help you work more smartly. Ignore my English, but that's the idea. Does that make sense? Okay. That will go into effect now. Okay? And it goes into effect, I will do it. Okay? Meaning that mastering physics will not. Okay? So mastering physics, if we're at 15 problems and mastering physics is still going to say you didn't do so many, your score is something. But I'll look at it and I'll say, did you get to 75%? What's 75% of 15? Would be 8? No, I don't think it's 8. You think it's 10? I think it's 10 I know is, but 11 is too. Yeah, 10 is not quite enough. 11. 12, you get 12 questions out of the 15, so you skip 3. I'm good. Okay? Yeah? Okay.
Pokemon.
Other reminders. There is the Simple Harmonic Motion Lab due. A couple of groups have sent in a draft, and I've got back to them. The rest of you either have brought one in today or have not. I would recommend it.
These are the ones you've done?
It's usually a good idea. I give free feedback. You can incorporate it into what it is that you're handing in, and anyway, if you,
that's pretty cool.
I will do a 24-hour response time, okay? Meaning that if you can get it to me by Friday night, I will give you a response by Saturday night. Now, Saturday night's kind of, well, anyway, try and get things into me either today in lab or by Friday morning so I can get something back, so I can work on it, say, Friday afternoon or something, and get back to you in a reasonable time so you have some time to use the results. Yeah?
I didn't get it.
Okay. All right. I will hand back.
Yeah, just ate Chipotle. So awful.
I love Chipotle. I thought I had
I'm gonna start.
problems. I never ate their food just in case.
Did you just
You never know.
What the E. coli thing? Oh, that's E.
It's happened
the
too
old
often
one.
to them, so. Yeah.
Oh, my,
Till now.
my brother actually.
Sucks.
He just moved back from Korea.
Ready?
Oh, it's so hard.
You know, look at my score.
We did a recommendation from him.
Oh, we get that. Did you use any words or
I have nothing. What's the next homework? I feel like instead of cutting out mastering physics, you should have just got down the floor.
Yeah. Well, I think Once we start the lab and he's wandering around, but what about
So I
that?
probably bring back mastering physics, but it's
Brandon?
very small labs.
You didn't enjoy yesterday?
I enjoy spending time with you, but not doing good things.
Justin?
Thank you.
You're welcome. Justin?
We just had a
So what's your dinner with him?
and it sucks. Yeah. It was actually like pretty hard. No, but like the thing is like
What kind of questions did it ask?
just practice once you get like you find it and practice it.
Was the exam a lot like that?
Yeah.
I feel like it might be okay considering I like the topic so much that maybe I'll be more motivated to watch TV.
Oh yeah, no, it's a fun class, you know. But yeah, like once you get you just gotta like, do everything like efficiently. You know, like the minute you get your you just
Would you cut its cat?
oh yeah.
This guy does amazing push-ups.
Right? Because I do all study I felt pretty confident except for my yeah, once I got there,
Every time I feel ready for the exam, I get scared because usually when that happens, I do bad.
but yeah, no, I know what I did. Like, I took my
That
time,
probably tires you out.
but like I took my time in the beginning of the quarter,
Uh-huh.
and so like I went really slow.
Oh, so when I research, it says like you see the CP the number, the CP number. The CP number is like higher than is better, stronger. Yeah, like
You
you
used to do
see
that
like
for gymnastics practice.
different PG, like they have different CP. Like CP means
What's the CP for coffee?
5.5. Oh, mine is 112. Oh, my easy is good. 71.
We're gonna do more with some standing waves. This is the last time I'm gonna use this big spring.
Oh, yeah. And like depending on the weight and the height, see my weight and height. Extra large.
Stream to
And
chat.
it's big.
As long as people don't.
Well, I don't know. I'm still.
Come on, chat with me. You get picked.
So,
Have you been there?
we have seen that by shaking this spring back and forth, we can get standing waves on it, okay? And we talked a little bit about them. We talked about how you can think about them as two traveling waves coming at each other, and that physically that makes sense, okay? That if I shake this, it's like sending a traveling wave down, and the waves bounce off the ends, okay? So if I've got two traveling waves that are going back and forth at each other, bouncing off the ends, they interfere, okay, to make standing waves.
After you roll it, the CP is even higher.
Now,
Try to having the highest CP.
it turns out that I can shape this in a lot of different ways, but not every frequency that I shape this with will make a standing wave, okay? Then there are certain special ones, okay? When I say I'm going to make a standing wave that goes at the fundamental frequency, okay, the one that goes like this, I can't shape whatever I want, okay? That makes different things, okay? And in fact, just arbitrary shaking, okay, makes a mess. Okay, that the standing waves are only certain special frequencies. Okay, so you can think about, well, how would I figure those out? Okay, and like we can think about how we figure them out and why they occur. Okay? So, the fundamental frequency is going to look like this, where the string goes back and forth like that. Okay? So it's going back and forth like that. So, if we think about this as traveling wave, the traveling wave has to have this shape in order to do the going back and forth like this. Okay? In other words, it can't be something like that, because over here, it would have to shake up and down, okay? And it can't shake up and down because that end is fixed, okay? So that end is held still. So in order to get the standing wave to give the reflected wave to come back, and then the next reflection to come back, so that it makes the peak right here, it's got to be a particular wavelength to make this work, okay, or a particular frequency and wavelength, right? If you remember, velocity is frequency times wavelength. So if the velocity is determined by how tight the spring is and what its mass density is. The important thing is if it's in a situation like this, that velocity would be constant because the tension isn't changing, the mass density isn't changing, so the frequency and the wavelength is related. Okay? Now, all right, so this is not allowed because this can't happen. If we have to have our nodes, our places that are fixed, be here, okay, then that puts constraints on what the wavelength is. Okay? Then we could say, I'll erase this one because it doesn't happen. Okay? But we could say, well, this is, our waveform looks like this, and that's half the wavelength. The full wavelength is it comes over and then went like that. So this distance would be half the wavelength. If we say that is the length of the string, we could say lambda, the wavelength, okay? Well, this distance is half a wavelength, so the wavelength itself is twice this distance. It would be 2L, right? Okay? That's the same as L is half the wavelength. Okay? Now, the next pattern that we can get, okay, is the next pattern that we can get goes like this, okay, where we have a node here, okay, a node here, and a node there, okay. So, well, let's say this has a node here, and an antinode. Okay. The next pattern looks like that. These are going back and forth. Those are going back and forth. Those should meet. Okay. We have a node here, a node here, a node here, an antinode, and an antinode. Okay. These ends have to be nodes, so the only way that I can squeeze in more loops is to have another node in the middle and then two antinodes over here. In this case, this also puts a restriction on, there has to be a particular wavelength for this, right? I could say lambda is equal to L, right? Because this is a full wavelength. You go all the way around and come back where you were. Yeah? Okay, cool. I can keep going with this, okay? And it's worth doing to see if we've got a pattern here, okay? I've got two ends. What has to be here? Nodes. Yeah, those are nodes. Good. Okay.
Equal to,
The next
just
more complicated one would look like what?
1.5 wavelengths.
What?
1.5 wavelengths.
1.5 wavelengths, that's right. Yeah, it would start here with the node. And it's got a node, and then antinodes over here, antinodes over here, and antinodes over here. Okay? So, imagine that's more symmetrical. Okay? But yeah, so that's what goes on there. And lambda is what?
Wavelength.
Lambda is the wavelength, and in this case, what part of L? Is it L? Is it 2L? Half L? 2/3, right? Because this is, we've divided it into 3 parts, and 2 of them, okay, give me the wavelength, right? So lambda is equal to 2/3 L. Yeah? Okay. Next. Okay. I'm writing these formulas down, but you know the pattern, right? Okay? And I'm going to say that we're going to end up deriving a formula. Okay? We'll derive a formula sort of from inspection. I don't want you to focus on the formula. I want you to focus on the method used to find the formula. Okay? Okay? And I'll tell you the reason why. Okay? The method using to find the formula is more general. Okay? And I'm going to use it again in a different situation. I'll use the same method, different situation, we'll end up with a different formula. If what you're remembering is the formula, you'll have to remember 2 plus others for other situations I haven't given you. Yeah? Okay? If you remember the method, then you know how to do it, even if I give you a different situation that you haven't seen on either the homework, or I'm giving a big hint here, okay? Or, so I'm not good at winking, but I would wink, okay? Now, if I were making an exam question, I might think a really good idea would be to put a situation where you could apply this method, okay, and figure out a formula, okay, figure out, how this is working without it be, so that you could use it, okay, but not memorize a bunch of formulas. I want you to memorize the technique, okay? Does that make sense? Okay, yeah. Do I have your attention now? Yeah, okay. All right. Cool, okay, so the method is the boundaries determine that I have to have nodes here, right? Okay? And if I have to have nodes here, then the next pattern is to sneak another node in the middle. Okay? So I'm going to have a node, node, node like this, and it's going to go I got enough? Yeah. Right. So now I've got 4 lobes here, and lambda is equal to, well, it's half L, 1/2 L. Okay, so you go, these kind of look kind of weird. We got a 2/3, we got a 1/2, we got a 2. How do we relate them all? Okay, it turns out that that finding that form, actually for me, okay, if I wanted to, if you know how to do this, I would say you have figured out how to figure out what the wavelengths are for standing waves with these conditions, okay? But as far as finding the formula, you gotta sort of inspect it and you get a little lucky, okay? One of the things, when I notice this 2/3 L, I say, this is, it's the size of this chunk, okay, that I'm looking for. This is, here it's 2/3, here it's 1/2, here it's the whole thing, but 2L is a big part of it, okay? And this is the first pattern, second pattern, third pattern, fourth pattern, okay? So the way everybody does it, the way everybody does it is they go, well, mode is equal to 1 here. This is the second pattern. M is equal, that's the third pattern, and M is equal to the fourth pattern here. And then you'll say, well, I could then say that this is, well, 2L, okay, over 1, okay. This is equal to, well, it's L, it's just L, okay, but that's the same as 2L over 2, right? 2 over 2 is 1. This is 2L over 3, and this one over here is 2L over 4, right? Okay? And so you go, I think I know a general pattern. Lambda is equal to 2L over M. Okay, so if I said, well, gee, what's the wavelength of the 500th mode of this? You wouldn't have to count them out. You could just do that. Okay? So, does that kind of make sense? What if you wanted to know the frequency? What if you were saying, I want to know this because I'm making a guitar string, and I want to know what frequency it's going to oscillate at so that I get the right note.
Is that equal to velocity over frequency?
Exactly. If you want to figure out the frequency, you can take advantage, you can use this, right? So you could say that the frequency is equal to lambda over v, okay, the velocity of the wave, okay? And then you could say, well, and then lambda is equal to this. So you could say frequency is equal to 2L over M, okay, with the velocity here, right? Now that's the frequency. Okay. You could even say that velocity is what the square root of tension over mass density, right? Cool. Okay, so we can find the frequency and the wavelength of the different standing waves. Okay. Because, I'm just going to say something now, because it strikes me, you might go, why are we focusing so much on standing waves, okay? Why do we care? What makes them really interesting? And in less than a month, okay, well, much less, in like 3 weeks or so, 2 and a half. Okay, we're going to start studying atoms. Okay, and we're going to start looking at electrons. Okay, and we're going to notice that electrons have properties that are a lot like waves. And then we'll go, why do electrons do electrons do funny things around atoms, right? Some of you have taken chemistry. Yes? Okay? And in chemistry, you have certain energy states of electrons, and they only fit in certain orbitals. And you go, what's special about those orbitals? They're the standing wave patterns around the atom. Okay? And so, as you may know, the electrons have wave-like properties. Okay? Especially when you think about them as little tiny objects around an atom. And those electrons the reason they're sitting in their orbital is they're sitting in their standing wave state. Okay? And the standing wave states have little formulas that look like this as to what their energy is or what their radius is or that sort of thing. And in 3 weeks, okay, we're going to be looking at that, okay, and it'll be all standing waves again. Okay. Cool. Good with this? One of the things that we could do is that we could imagine that instead of the ends being fixed, okay, we have maybe this end loose so that it could move up and down. Yeah. Did I do my division wrong?
Yeah.
This should be right.
This one is wrong. Frequency equals MV over 2L.
Oh, right. Wait.
You should have divided lambda by velocity on the left.
I don't even know that so much just know that it's an honest
Right.
mistake. Just give me what you like.
In Japan.
Frequency. Oh, it should be velocity over lambda.
It's so annoying. I'm like, everybody knows what the algebra is. Just do it right on your own paper.
Better? Okay, thank you. It's hard to do algebra. Thanks for checking. I check yours too. I do, and actually, I am. I end up double checking to make sure, especially when grading. But doing it on the board is even harder. Okay, so that's better? Good. Okay, thank you. All right, so it's not always true that the ends are fixed like that, okay? It's possible that the end might be loose, okay? And you might be saying, oh, well, if the end is loose, how could it have tension, okay? And the answer is that if we just take the slinky and lay it out on the floor, it won't, okay? So I can't really demo this very well with this spring. But you could imagine if there were like a little lightweight pulley, okay? Or a loop of the spring that went around this that could slide up and down, okay? And it did so without, I've tried actually doing that, and the problem is the friction with the pole and the loop is pretty big, okay? But you can imagine something like that, okay? In that case, okay, when the pulse came, right now when the pulse comes down and it hits this, it ends up, it can't move this, okay? It can push against it, and when it pushes against it, the bracket pushes back, and it ends up sending a reflection pulse back that way, and it ends up being reversed because, well, when something comes in here and pushes up, the bracket pushes down, right? Okay, when you push down on the bracket pushes back up, and it reverses that pulse. But if this were open, if this could slide up and down, okay, then it wouldn't push back the opposite way, it would just follow along with it. In that case, what happens, the reflected pulse that comes back is the same shape, okay, or it's turned around, okay, what initially comes in is up. Then what's reflected up has its initial leading edges up, okay? And it doesn't reverse like we saw with this edge. Okay? If we had let's imagine that I had a loose end over here and a loose end over here, what would the standing waves look like? Well, situation. We've also talked about sound waves. Okay? One of the things you can do is you can okay. You can do something like take a tube, okay, and sound waves can travel through the tube, right? They can go back and forth, okay, inside you. And when you think about a sound wave, I'm like compressing the air and expanding the air quickly, and those pulses can go through the tube, okay? When they go through the tube and they get to this open end, okay, well, that's like what I described, right? The wave pulse comes in. Some of the, let's imagine the high pressure part comes in first, and it leaves the tube, okay? So it leaves the tube, and now there's a partial vacuum in the tube. It gets sucked back in the tube, okay? And then there's a reflected pulse that goes back down the other way, yeah? And it could leave the other end and reflect back and go the other way, okay? So this is the same idea as an open boundary, okay? Where, like with the spring, or with the pulley going up and down on the rope, the air can go in and out of this, okay? But it would reflect. And I can set up standing waves. If I blow across the top of it, okay? It's kind of low, because this is a long pipe, okay? But I'm sure you heard a frequency here, okay? That's a standing wave. I can't get, if I blow across it at any speed, I get that, unless I can get a harmonic. I don't think I can get a harmonic. Okay. All right. Okay. Let's think about what those look like. In that case, what I've got is a tube that looks like this, okay? And instead of having nodes at these ends, okay, because it's fixed and the air can't move, the air actually can move at those ends, okay? And so it turns out these are going to be the antinodes. This will be a node, and that will be an antinode. So,
Is that the pipe?
that's a pipe. So maybe I'll go. The pipe is in red. Okay? And then the waveform might look like this. Okay? So this is an antinode, a node, and an antinode. Yeah? Okay? So these are going back and forth like that, and these are going back and forth like that. Okay? Well, if I have this, that's half a wavelength again, right? Okay? So this is half a wavelength, and I would say that the wavelength is equal to 2L. Okay? Sort of like before. But now I've got my pattern with my nodes and antinodes. If I draw the next, oh, the pipe is red. The first harmonic, okay, would look like this. It would have antinodes at the ends because these are open, and instead of having one node in the middle, we can put two in there. So like this, and then an antinode like that. Okay. So these are going back and forth. Okay. And now this length of the tube is a full wavelength. Okay. It matches like that. It turns out that if we keep going with the open tube, we're just going to reverse this pattern. We'll have antinodes here, antinodes. Instead of 2 nodes in the middle, we'll have 3. Node. That, okay, and now we have, I did this one, didn't I? Did I?
I'll think about it. Just like,
Oh, yeah. No, see, this is, no, I did this right, okay? This is, a full wavelength is over here, which is 2/3 of the length of the pipe, right? So I could say, say that's a third, that's a third, and that's a third, and 2/3 gives me 1 wavelength, okay? It continues on, okay? So it turns out that the formula for these different patterns, okay, is determined by where the antinodes are, how many nodes and antinodes I can fit in the middle, and the formula turns out to be the same as what it was when both ends were fixed.
Question.
Yeah.
I'm unsure about what you said, the boundaries and open boundaries, or what happens.
Okay.
So I'm assuming the boundary one, they just, invert, as it bounces it off.
Okay.
Yeah.
Well, Ken, I think your question is, what are the 2 types of boundaries? I mean, specifically, and then how do the waves reflect?
Yeah.
Okay. So the 2 types of boundaries is either that it's fixed. Okay. So fixed would mean that when the wave hits there, whatever the medium can't displace it. Okay. So if it is if it's on the spring, it's like this clamp that's holding it down.
What do you mean by medium?
The spring itself.
Okay.
Okay? So the spring, if this part of the spring moves up or down, it can move its neighbors up and down as well. Right? Okay? And that's the process by which the wave goes through the medium. Okay? I'm using the language here. Okay? That's the process. Okay? And then, but when the wave hits this boundary is fixed. It cannot move up and down. Okay? So when it hits, no matter what, okay, it's got to, the spring itself is stuck right here. Okay? It can't slide up or down. Yeah?
Yeah.
Okay? So if I've got a standing wave, the only kind of standing wave that's going to work, okay, is one where there's a node here. Okay? Because that can't move. Okay? If I try and set up a standing wave here, okay, and so things are moving in and out, this will need to be an antinode. If I'm making the wave go by pushing some stuff in and out, I've got to be pushing it in and out a lot up here. I can't push it in the middle because I can't get there. Okay? So this is going to be an antinode. This one will be too, because the air is going to go in and out. And so I can figure out what my patterns are by saying that because this pipe has open ends, okay, my antinodes have got to be on the ends.
So in order to make sound, you need to blow in the smooth side, right? Because of it.
I was blowing Well, yeah, that's where the anti-nodes are. Yeah, and when I do blow on the top, some air's going in and coming out, and I'm setting up that pattern going back and forth. And air's gonna come out here and go back in. Yeah?
Yeah, I see.
Is that kind of it?
I get it, but I don't see why it's important or
Why it's important? Okay.
not like that.
Okay, well, okay, let me, another,
I don't see that there.
okay, well, I'm getting there, okay? So, we talked about how I can't really make one of these boundaries open because I don't have the right equipment to make that work. I don't have something frictionless enough that can hold tension, okay? And it's lightweight enough. But it turns out that with a pipe, it's pretty easy to make it enclosed. All you gotta do is put a wall there, okay? Once I put a wall there, it could be my hand or something else, then when the sound comes down, it can't go out the hole and then get sucked back in. But instead, as it pushed against the wall, okay, if the pressure was coming in and hit the wall would push back, okay, and this would behave like a closed boundary. Okay? Did you have a question? Oh, okay. All right. So with the tube, I can make it open in a closed boundary. I can actually do this pretty easily with a couple of pieces of tape. If we had tape. We don't have tape anymore. Do you see tape? Oh, yeah, perfect. Thank you. Cool. No problem. Who knows how it ended up there? But thanks for finding it. Oh. So that's both ends open. It's even lower. Okay, I'm really, okay, but that's one end closed. Okay, so it changes what's going on. Okay, now this is an antinode. I'm blowing in and out, but this has become a node. Okay, so I'm going to get a different pattern. Let's look at that. The pattern we're going to look at now will be the one that you'll use in your formal lab in a bit. Okay. So here's the pipe. Okay. One end is closed off. One end is open. Okay. What has to be at this end? A node. And at this end? The antinode. Okay. Turns out we can set up a standing wave that way. It would look like this. Right? So this has got its antinode, it's got its node. Okay? In that case, what fraction of a wavelength is this? Or here's L, the length of the tube. Okay? It's a quarter. Yeah, it takes 4 of these, right? If I had another piece that looked like that, it would come back down to the middle, and then I've got to repeat again. So that's, well, lambda is a quarter of a wavelength, or lambda is equal to 4L, right? Okay? Now, what's the next pattern I can do? This has to be a
No.
No, yeah. This has to be a antinode, okay? So here I just went from antinode to node. If I want to add some extra stuff, I'd have, after the antinode would come a node, and then an antinode, and then I could be back at the node, okay? So this would look like this. It would go to the middle spot here. Like that. Now, how much would, well, if I were here, L was a quarter of a wavelength, or the wavelength was 4L, what's my relationship here? We have to do a little algebra. I'll try. Is that a wavelength?
3/4.
It's 3/4 of a wavelength. Right. So you can say L, the length of the tube, is 3/4 lambda. Right? So this is half, that's another quarter. Okay, it's 3/4 lambda. So you could say lambda is equal to 4/3 L. Right? Okay. And if I draw the tube again, okay, okay, and I say I want to go the next one higher. Okay, that's got to be an antinode at the open end. Okay, that's got to be a node over here. Only instead of sticking another, I can just stick another set of nodes and antinodes in there. Yeah. Okay. How many wavelengths do I have here?
1/4.
1 1/4. 1 1/4. 5 quarters. Oh, 5. L is 5 quarters lambda, right? So lambda is equal 4L over 5. Okay? So here I've got 4L over 3, 4L over 5. Without drawing this one, what do you think the next one's going to be? I saw it whispered. 7. 4L over 7. Right? Okay? So we see this pattern. We keep adding these these extra chunks. Okay? And so we divide. Here's a quarter of a wavelength. Here's 3 quarters of a wavelength, 5 quarters of a wavelength. Each time we add another 2, okay, and we have that extra quarter at the end. Okay, so this is a different formula than we had before. The other thing is, when we were labeling our modes, we called this 1, 2, 3, and 4. Okay, and with the other pattern, and now we could get our formula to work if we called it m is equal to 3 and m is equal to 5. Okay? And you might go, that's convenient, it looks nice, but how would I know? Or what should I be thinking to describe this? And your book does something that I thought was not It says, well, you count the antinodes in one case and the nodes in the other. And this, and if you do this, it works. And it seemed kind of awkward. Okay? But if you go back and look at the case that you had before, so there are two ways that I will address this. First of all, I will not be picky with how you label these things. So if you label them 1, 2, 3, 4, and 5, and worked out a formula to make it work, I'd be happy. Okay, especially if you showed me how you did it, I'd go, all your fundamental physics is fine, you're just labeling things differently. Okay, so, and it can be kind of funny. Okay, the other thing is that in all of these cases, if what you say is that the pattern that, and I'm going to maybe quickly over here redraw those shapes for the standing wave, because they're really okay, like that. If you say, all right, whatever I get in my fundamental state is going to be my initial shape. Okay? So over here I have one of my initial shape, right? Okay? Over here I have one of my initial shape. Yeah? Now, how many of my initial shape do I have over here? I've got 3, right? I've got the initial shape is a node to an antinode, okay? This node, this open spot to that closed one, and I've got 1, 2, 3, right? So you can say I've got 3 of my initial shape over here. Over here, that's my initial shape. I've got 2 of my initial shape, okay? So if you say, all right, the way I'm numbering these things is based on whatever it was in my initial shape, then you can say that's m equals 1, m equals 2, m equals 3. And then over here, it makes sense to make that be 1, 3, and 5. Okay? If you do it that way, your formulas will work out easier. And yeah, it's right. Okay. Good? This is kind of an interesting shape, okay? Where you've got actually a lot of musical instruments are made from tubes, okay? One of the things you can do is change the effective length of a tube with valves, right? So things like flutes and saxophones and stuff like that have valves. Another thing you can do is you can change where the end is, okay, of the tube. So I've got this, which is a tube that's got, you can't see inside because it's I don't know, I think it's a painted aluminum tube, okay? But it's got a plunger that I can move up and down, so I can change the length, okay? It's also got a narrower end that's easier to set off base vibrations. And I can blow on it and get a particular pitch, okay? But I can change the length of this. Okay, I'm not going to be a great musician with this. Okay, but you can tell that as I'm moving this around, okay, yeah, you can change the pitch. Okay, so I guess a trombone works that way, right? Where you slide you lengthen and shorten the tube, okay, and get these different standing rates in it. Okay? All right. There are a couple of other things, a couple of other little things that I want to clarify from previous chapters. Okay? One of them was, and this also came about from discussions at homework. First of all, I wanted to say, I assume that you're reading the most of the master and physics problems are out of labeled sections. You know, so I assume that you would go to that chapter and look at things. One of the things that was in the previous chapter, I think it was 15, was a discussion of different types of waves. And they did the waves on the spring, they did water waves, but they also talked about light waves. Okay? And I want to address that in a little bit. Okay? You might go, gee, how did you leave out light waves? Aren't they kind of important? Okay? Yeah, it turns out they're so important that that's almost all of what we're going to do in the next few weeks. So I was thinking, this will, basically I think all that chapter 15 says is, by the way, light is a wave, okay? And it travels very fast. Okay? So as far as what to get out of chapter 15, okay, light is a wave, okay? It travels at the speed of light, which is a known thing. I think on your formula sheet it has v sound, v light, okay? So the speed of light is it's 3 times 10 to the 8 meters per second, or about 300,000 kilometers per second. Okay? In miles per hour, no, I don't know. In miles per second, it's 186,000 miles per second. Okay? So it's really, really, really fast. When we did our fireworks problem, we assumed that light traveled instantaneously, and that's over the time scales, 6 seconds. It's really, really fast. Over astronomical distances, it begins to matter. Okay? So light is a wave. It travels very fast. It has a known speed. It also travels spherically. Okay? So like sound waves that decrease in intensity, light waves would decrease in intensity the further you get away from them. Okay? You know that if you look at a car headlight, and you look at it a meter or 2 in front of it, it's incredibly bright, right? And if you look at it a mile away, it's much dimmer, right? And it spreads out like sound, okay? In a spherical way. Good? Okay. Yeah?
I have a question on the board. Is it flipped? Like a closed end is supposed to be the antinode and the open end is supposed to be the node?
I thought the open end was the antinode. Because
The book has it flipped.
the book has it flipped. Okay. I could have it flipped. Okay. They definitely have different properties. Okay. With the closed end, okay, it's the air is swishing up against it and then bounces off. With the open end, it escapes and then gets sucked back in. Okay. Okay. I suppose I could have them flipped.
I thought it was a rule because it has it enrolled in the closed end of an air column as an antinode pressure. So I didn't know if it was a.
Okay. I would. It may be. Okay. It wouldn't change what these results are. Okay. Okay.
For 544, lambda, or
Right?
yeah, lambda, is it n equals 2.5?
Oh, for the mode?
Yeah.
No, it'd be 5.
5?
Okay? So you'd say, here's our fundamental shape, and I have 1, 2, 3, 4, 5.
How about resonance? This textbook said Renaissance waves.
Resonance?
Is
Oh, the
that-
standing waves are a form of resonance. Okay? So, if
Well, what I'm trying to say is that the textbook, it reads that how your interpret is different from this textbook.
okay,
And
in what way?
that each loop is equal to 1.
Yeah, I know. I told you I thought their numbering scheme was crazy.
Oh, okay.
And if you can make it, don't they call this m equal 5?
No. What's it?
Oh, that's a different, that's got closed ends. Okay? But it's, so here, they go 1, 2, 3, 1, 2, 3, 1, 3, 5. Right? So, this is the sort of thing I'm looking at. Okay? And they've got too many rules, I think. Okay? In coming up with that description, and I'm advocating take your fundamental shape, and then this has one of the fundamental, all the ones has one of the fundamental shapes. This has 2 and 3, and then this has 1, 3, and 5 of that fundamental shape. Yeah? Okay?
So with open you apply each chunk.
With open, you apply each chunk,
No, with open ends,
right?
you count this as one. The way this closed is different.
There's a lot of rules here. You can follow those, okay, if you want. And I tried to, and I couldn't make too much sense of it. Okay? But the way I've always thought of it is if you look at your fundamental and say that's my fundamental shape, okay? And then if I want to count what mode is next, I count how many of the fundamental shape are in there. Okay? All right. Okay. The last thing I want to talk about before we do our Speed of Sound lab is my second attempt to do the Doppler effect. Okay, and I think I'm ready here. Okay.
Drummer? Are you a drummer?
Everything. Guitar sounds. I do rockers by tilt.
Nice.
Forget sideways, I really mean it.
Inaccuracy.
Okay. So.
Oh my gosh.
All right, this is a car driving by a laptop at 10 miles an hour. Okay. So you heard it was kind of higher pitch. When it passed, it dropped. Okay. So now, here's 20. Oh, sorry, that's 30. Okay. This is 20. Yeah, so it's higher pitched, drops when it passes. Here's 30. Yeah, so it's even more pronounced at 30, and the last one's at 40. Yeah. Okay. So there is Doppler effect.
Yeah, and this comes like just like Pokemon, right? Okay, all the Pokemon, Zubat, all these come.
Yeah.
It's always Zubat.
But you don't need it.
Yeah.
You think I got it right? Yeah,
Are you just tired or you don't feel good?
okay.
It's a big combination
I
of
know
things.
the patterns and the behavior, the frequency and the wavelength.
Yes.
What? What is the highest?
Is it that?
I'm not gonna take a nap after. Do you let's go home?
Like to take a nap
Let's
after
go home
you
and watch more.
Anyway,
I'm gonna go run. I'm gonna go walk around.
Could be before, could be after, could be all day.
That's usually what I do Saturday.
I
Sleep
like to
late.
relax after I eat, like I'll watch TV.
Mm-hmm.
I'll certainly fall asleep, but I'll be a TV coma. It's okay. I was just playing with
Just a joke.
Whenever you go to a team, you can choose what team you want to be.
Oh yeah.
You choose yellow.
You choose yellow?
My friend.
I don't know.
You choose yellow.
Okay.
Can you do Jigglypuff?
There's actually Jigglypuff's in Factorio. So Joe goes to Factorio.
I was thinking about it.
Join the yellow team. Join the station.
You just have to like go places and go find like Pokemon.
You can't fight people though.
It's like
You can't
geocaching.
fight
Okay.
people.
So we're gonna do the speed of sound lab. It's a formal lab. It's our second. We have to do 4 formal labs. And we've got 7 weeks total. And it turns out that there aren't that many formal labs we can do with the quantum and nuclear physics stuff. So they're kind of bunched up in the beginning. Okay, so it's just how it goes. On the other hand, as the quarter winds on, okay, those will at least be out of the way. Okay? Okay, so this one's going to be due Tuesday, July 19th, okay, which is a week after the exam. Okay? And we're going to do 2 things. Okay? One of them is that we will estimate the speed of sound, okay, by looking for standing waves in tubes. Okay? So we're going to have a tube with a, I'm going to draw like this. We're going to have a tube where we can vary that bottom, right? Okay? And so we can change this length, okay? And we're going to set up standing waves in this tube. What are the standing waves going to look like? That, right? Okay? So these standing waves themselves, somebody was mentioning it's a resonance situation, okay? Meaning that in order to get the wave to happen, you've got to drive it at the particular frequency that the standing waves occur, right? I showed that with my hand, in generating those standing waves on the string. If I shook at a particular frequency, they appeared, okay? And if I was off that frequency, I got other stuff, okay? So what you're going to do is shake the air at a particular frequency. Actually, you'll shake the air at a particular frequency, and you'll raise and lower the bottom and look for the resonance. Okay? So the equipment here looks like this. Right? We have these plastic tubes, okay? And then we have these cups and a hose, and you can add water here and change the level of water in the tube, okay? And you have an open end here that you can apply a particular frequency to, and you'll listen for the tube resonating, okay? So how are you going to apply that frequency? Okay.
Wind chime?
we have a set of tuning forks, okay? And the tuning forks vibrate at a particular frequency, okay? Now, there are a lot of ways you can get them to vibrate, okay? But they're made out of aluminum, okay? So some of the ways I don't want you to do, okay? I'm happy with you whapping them with the palm of your hand, okay? There are these little mallets, I guess, that you can work them with. But I don't want you to hit them with hard things, like the table or the floor, okay? A lot of people find that using their leg, well, maybe not, works pretty well. I don't mind if you use something, it's not. But I don't mind if you use something like that, but something soft, okay? We have plenty of these, okay? Any body parts should be good, okay? But not tables, not other things, not any of the tubes over there, or something like that. Okay? They're labeled, this is 256 cycles per second. So if you were to hold that over this, okay, then you would know that, and it resonated, okay, the tube starts to sort of amplify that note, okay, then you would know that there's a standing wave that you can create with 256 cycles per second. Okay? What does it look like? Probably this one, or that one. Okay? In fact, the lab manual sort of has you try, if you just hit one, you don't really know which one it is. Okay? So suppose you hit one at 30 centimeters. Okay? If you hit one at 30 centimeters, you go, it might be this, right? And I'm getting, and it might be this one. And in that case, I would expect at 90 centimeters, I hit this one. So you could try 90 centimeters. Or you might say, maybe I hit this one at 30 centimeters. If you hit this one at 30 centimeters, that would predict that at 10 centimeters, you'd hit it again. Okay? So what you're going to do is when you find one of these resonances, you're going to have to figure out if it's this one, or that one. Okay? And actually, while you're doing it, you can record the data. We got a resonance here, here, and there to sort of help nail down where those work. Okay? So from that, you can find the wavelength. You know the frequency. It's the frequency of the tuning fork, and so you can get an estimate for the speed of sound. Yeah? Okay? These would have uncertainties. This is probably at least plus or minus 1 hertz, and this uncertainty will be based on how well you can hear the resonance. Okay? You can measure to millimeters, but you might find that your determination of where I am on resonance might be plus or minus 2 or 3 centimeters. Okay? Depending on how sharp the resonance is. Does that make sense? Okay? So if you find it at 30 centimeters, and you find it at 31, and you find it at 32, but you don't find it at 33, then you might say that's 31 plus or minus a centimeter. Yeah? Because it's somewhere in there. Good? Okay, so that's the first thing you do. Okay? And that should give you an estimate of the speed of sound and an uncertainty in the speed of sound. Okay? The other thing you can do is we're going to take these pipes, and it turns out you can make a pulse, okay, and the pulse will echo back and forth. Okay? You can measure the length of this pipe. If you could determine how long it took for the sound to go from one end down to the other and come back, okay, you could get an estimate of the speed of sound. So, but in order to do that, you'd have to have really good eyes and a really good clock, okay? So, to do that, what we have are these microphones, okay? And the microphones, you can set at one end of the tube, okay? And you can do things like make a little sharp noise here, snap your fingers, people have banged weights together. There are things you can do to make a pulse, an audio pulse, okay? And then the pulse should travel down the tube, reflect back, and reflect back, and reflect back, okay? So you can check that out. You can look for the signal with the microphone. If you want, you can change one of the ends from being open to closed. We have these munched up styrofoam cups, and a lot of them are set so that they fit pretty tightly over the end, okay? If you need to make a new one, I don't think you do. I think we've got plenty, okay? You can stick one over the end, and now you can say this end is closed, and send signals and watch for their reflections, okay? Good. To do that, you'll need the Lab Pro and that sort of thing. I think in the 116 folder, there's a speed of sound file that'll help you take that data. Okay? And again, you should be keeping track of, you measure this length, what's the uncertainty in the length, you measure your timing, what's that uncertainty, plus or minus so many milliseconds, and that'll give you a velocity of sound. And then you can compare it. Seem okay? Okay. Now, here is the biggest challenge with this lab. We have 4 things with the water, okay? And we have 4 microphones. And we have 6 lab groups. So I would advocate that maybe the people in the front do the water, and the people, wait, hang on. If you have a, is everybody, hang.
We could just do bigger lab groups.
It helps if you're going to do water to have a hose, okay, attached to your faucet. So you guys don't. You should do the sound thing first, okay? And but it looks like the rest of you have. Okay. So I'm thinking let's have 3 groups. Maybe the 3 in the back do with the water. So all 3 in the back have the hose, and the 3 in the front set up the microphone. And then let's arrange some trades. I'd say just go with, swap with the people in front of you, but I want to work efficiently. So when you finish your activity, whatever you start with, the water or the hose, let me know, and I'll broker a deal with somebody who's finished with the microphone thing, and we'll swap. Good? Okay, the rules are, if you, and I realize this is kind of a little weird here, but set up one thing, and then clean up the other one when you're done. Okay? So if the guys in the back, you'll set up the water, okay? And then you'll clean up somebody's microphone stuff. And the people in the front, you'll set up the microphone stuff, and then clean up the water thing. Okay? Good. All right, let's speed it down. Good.